Good morning to everyone. Today we are going to see about the Unit 5 in Communication System, Linear Block Coding and Convolutional Coding. So here in linear block code, before we need to say the error control coding. So what is error control coding? So under the error coding, control coding only, the linear block codes and convolutional codes are there. Okay. Then so first we see about what is error control coding, why we need the error control coding. Okay. So normally in a transmitter side, in a transmission and reception side, the error and noise is the main problem in the signal. Okay. Once we are transmitting the signal from transmitter to receiver or sender to receiver, in between some noises and error will occur. Okay. So this is the main problem in the signal. It disturbs the reliability of the communication system. Okay. So error control coding is a coding procedure to control the occurrence of errors during the transmission. Okay. So these techniques help in error detection and error correction. Okay. So there are many different types of error correcting codes are available. So, but historically we can classify it is into two types of error control codes. The first one is linear block codes and convolutional codes. Okay. So how to correct the error using this error correcting code means here see this figure. Okay. So it's clearly mentioned the error correcting code. So here the first one is message. So correct original information. Okay. So after that we are encoding this message original information bits. Then it is transmitted. So encoding means here transmitted code word. That means the input message added with one code word. Okay, mixed with one code word. So that is the transmitted code word. So that is also called the redundancy bits or parity bits. Okay. Then it is the received code word contains the message plus code word. Then we have to recover or correct the code. So this is the bad design because this is the received signal. It contains noise. Okay, noise and errors. Then we have to remove this noise using the correcting code, error correcting code. Then so once using this error correcting code, we received the good design, the original information sent by me. Okay. So this is the input and this is the output by using the error correcting code. Okay. Then what is linear block codes? Okay. So here in linear block codes, here we are using parity bits or check bits. Okay. Parity bits, check bits and message bits have a linear combination. Okay. So it is a redundant code word is the linear combination of any two code vectors. Okay. So the linear block code contains both message bits and parity bits or check bits, which is have a linear combinations. And the resultant code word is the linear combination of any two code vectors. Okay, so once we can add two code vector, it produces the another code vector. That is called a linear block code. Okay, then here we can consider blocks of data because it is a block code. So we can consider it is a blocks of data. It contains k bits in each block. So k bits means k number of message bits. Okay. So these bits are mapped with the blocks and n bits in each block. So total length of the block is n. Okay. K it's number of bits in the message. Okay. Then here n is greater than k because the k include message bits as well as the check bits or parity bits. Okay. So both are the total length of the block, that is n, small n. So the transmitter add the redundant bits which are n minus k bits. Okay. So I already told the block include message bits plus check bits. Okay. So the message bits are small k and the check bits are, it is here it is n represents the total number of bits. So here n minus k, that means the total number of bits minus the message bits. Okay, so that is the redundance bits or check bits. Okay, so the check bits it's equal to n minus total number of bits minus message bits, it is called check bits. Okay, so the ratio of k by n is the code rate. Okay. So here, for example, k is the number of bits, it's 3. And n it is equal to 8. Now it is 3 by 8. It is the code rate. It is denoted by a small r. So this is the block diagram of linear block codes. Here see that the input is the message bits and it is applied to the channel encoder. It encodes the message bits. So here the message bit with the code word and the output is the code block. Okay. So what are the inputs here? Only the message bits, k number of bits. The output is the total n number of bits. It's include message bits as well as the check bits. So this check bits, it is called, it is n minus k, total number of bits minus this message bits. So it is called a check bits. So the principle behind the linear block coding is here we know k number of bits, then n minus k parity bits or check bits are added. So hence the total number of bits in the encoder, it is denoted, it is n, small n. So such codes are called n comma k block codes. Normally we say n comma k block codes. That means 7 comma 3 or 8 comma 4. So likewise we mentioned the linear block codes. So this figure illustrates the structure of the only code word, because the message plus code word, it is message plus check bits called code word. Okay. So here this is the message bits and n minus k bits, these are the check bits, both are including in the code word. So the structure of the code word, it includes message bits plus check bits. Check bits means total number of bits minus the message bits, that is the parity bits. Okay. So this in linear block codes, n comma k bits. I already told 7 comma 3 or 7 comma 4. So likewise we mentioned. So n comma bits k, the bits are added here. That are the check bits. So this check bits help in error detection and correction. So this check bits are going to correct the error and detect the error. Okay. And also it locating the data. Okay. So now the data being transmitted here, in the code word, the leftmost bit of the code word it correspond to the message bits. Okay, we already know, see that the leftmost, so this the total block include, it is a code word. We say the total block is a code word. Okay, so here the leftmost bit is represents the message bits and the rightmost bit the bits are represent the check bits. Okay, that's why we tell about the leftmost bit of code word correspond to the message bits and rightmost bits of the code word correspond to the check bits. Okay. In the linear block code, there are two types of codes are available. The first one is systematic code. The second one is non-systematic code. Okay. Then in systematic codes, in the linear block code, here the message bits are appear in the beginning of the code word. The first, okay, that means the leftmost of the code word, it in the beginning of the code word, the message bits are appear. Okay, so the message bits are appear first. Then after that, the check bits are appear. Okay. So first message bits, then check bits that are transmitted in a block. So this type of code is called a systematic code. Okay. So the systematic code include the message bits appear first in the beginning of the code word, and after that the check bits are appear. Okay. In non-systematic code, the second type, in non-systematic linear block code, it is not possible to identify the message bits and check bits. Okay. We are not able to find out the message bits and check bits. Okay. So they are both are the message bits and check bits are mixed in the block. So we are not able to easily identify the, so these are the message bits, these are the check bits. Okay. So it is not possible to identify both message bits and check bits. So they mixed in the block. Okay. So this type of coding is called, so it is a non-systematic code. Okay. Then, so consider, so here the linear block codes, here how to produce the code vector. Okay. So already we say about a code is linear means the sum of any two code vector produces the another code vector. Okay. That's why it is called as a linear block code. Okay. So this shows the any code vector can be expressed in a linear combination of other code vectors. Okay. So here we can consider the code vectors. So the k number of bits already we told that is the message bits. Okay. So that represents M1, M2, M3 up to k. Okay, MK. So this is a message bits and C1, C2, CK. Up to this it is a check bits. Okay. So 1 to Q number of check bits. Okay. That represent in C and K number of message bits that is represented by the alphabet M. Okay, small. So this code vector can be written as this capital. So here see about the capital letter are mentioned here in vectors. Okay, the capital letters, the capital alphabet are, suppose here X means it is a code vector. Okay, this is capital M means it is a message vector. Then capital C means it is a check vector. Okay, a small alphabet represents, small m represents message bits. Okay, small c represents it is a check bits. Okay, but in capital X represents code vector, capital M represents message vector, capital C represents it is a check vector. Okay, so here remember this one. Here Q it is Qn minus K. So we already said Q it is a number of check bits. Okay, so number of check bits Q it is equal to total number of bits minus the message bits. So total number of bits here represented in small n and message bits represented in small k. So Q it is equal to n minus k. Okay, so where the number of redundant bits are added in the encoder. Okay, so we can represent the code word in terms of the code vector capital X, it is equal to capital M message vector bar, it is check vector. So it include this code vector include message vector plus the check vector. So that's why we mention X it is equal to M bar C. Okay. So M is the K bit message vector. C is the Q bit check vector. Okay. So the main aim of the linear block code is to generate the check bits, and this check bits are going to used for error detection and error correction. Okay. So this is the main aim of the linear block codes. Okay, then we are moving to the second one, the convolutional codes. So what are convolutional codes? So here the convolutional coding is done by combining the fixed number of inputs. Okay, so in convolutional code, the input is 1. Okay, the output bits are 2. Okay, only one input is applied at a time. Okay, the input bits are only one bit we can able to apply through the shift register, that is fixed. Okay, then there are two outputs are in the convolutional code. So the input bits are stored in the fixed length of shift. So these are the shift register M1 and M2. You assume these are the buffers or shift registers. So here the previous two successive message bits are stored in those flip-flops. Okay, so we can say this is shift register or flip-flop or buffer. Okay, so here the previous successive messages are stored in the shift register. It represents the state of the register. Okay, so this M1 and M2 represents the state of the encoder or convolutional code. Okay, so here this M represents this bit, the current message bits. Okay, once we are, so I already told only one bit at a time we can apply. Okay, so this bit represents the current message bit. This bit is the part of the shift register message bits in the input. Okay, so here these two are the modulo adders in the output. Okay, this is modulo adder 1, modulo adder 2. The two outputs X1 and X2 are the two outputs. Okay, so this, so here the input bits are stored in the fixed length of these shift register and they are combined with the two modulo adders. Okay, so this operation is equivalent to binary convolution, hence it is called the convolutional coding. Okay, so here K represents the message bits 3, K it is equal to 1 and N is equal to 2. Okay, so here 3 in M1 and M2, so there are 3 and the two outputs X1 and X2, that is 2. Okay, then what is the operation behind the convolutional encodes? Here, whenever the message bits is shifted to a position M, so that means the current message bits, and in the new values X1 and X2 are generated, it is depending upon the M1 and M2 M1. and this M2 stores in the previous two message bits. Okay, so the current message bit is present in the M. Okay, so that is the first bit. Okay, so what is the output of X1? This X1. So the output of X1 is here M1. Three inputs are came here in the X1. So this M1 and M1 and M2. So we can represent this is the M plus, this is the modulo addition. M modulo addition of, so M plus M1 plus M2. Here, this addition represents the modulo addition. Okay, it is a XOR operation. Okay, not a actual normal addition. This is the XOR operation, modulo addition. Then X2 represents, so here X2 only two outputs came from M and M2. So that's why we can write X2 is equal to M modulo addition of M2. Okay, so these are the two outputs. So the output switch first samples X1 and then X2. So the shift register then shift the contents of M1 to M2 and M2 M1. That means here, suppose the first bit came here now, it stored in the M. Okay, then in the first shift, this M moved to M1. Then M1 moved to M2 shift register and this M2 bit is discarded. So this is the operation behind the convolutional encoder. Okay. So that's why the next bit taken and stored in the M. Then X1, X2 are generated according to the new combination of the M, M1, M2. Because M1 it is shifted means the output also different. Okay. So the output switch then sample X1 and X2. Thus the output streams are successfully input will be, it is X, it is equal to X1, X2, X1, X2 and X1, X2. It is shown. So the combination. Okay. So these are the outputs. Okay. So here in input bit 2 encoded bits, it is X1 and X2 are the transmitter. So the outputs are transmitted to the input of the transmitter. Okay. So here the single message bit encoded code word is 2 bits and the convolutional encoder. So we already know it is a number of the message bits k is equal to 1 and number of encoded output is message bits, it is n is equal to 2 because only one bit is sending, we are sending at a time. So the input bit is 1, output bits are 2. Okay. Then already told the code rate is k by n or equal to k by n, number of message bits divided by total number of bits, it is equal to 1 by 2. So the code rate of the convolutional encoder is 1 by 2. Okay. Then the operation of the convolutional encoder. Okay. So in the first shift, the message bit is entered in position M. Okay. So first bit came now. This message bit first entered in the position M. Then the second message bit is shifted in M1. Then the third shift, the message bit is shifted in position M2. Okay. What is the constraint length of the convolutional encoder? Here, it is defined as the number of shift over a single message bit. Okay. The constraint length means here the number of shift. How many number of shift over a single message bit? That influence the encoder output. So it expressed in terms of message bits. Okay. So here the constraint length means here M, M1 and M2. So K is equal to here 3 bits. Okay. So this is because the encoder, a single message bit, it influences the encoder output for 3 successive shift. Okay. A single bit entered in the first shift, it will move to the next first shift and in the M1 and in the next shift it is M2. In the next shift it is discarded. Okay. So likewise, the output depends upon the shift of the input bits. Okay. So in the fourth shift, the message bit is lost. So that's why no effect in the output. Okay. Then we are going to see about the dimension of the code. What is the dimension of the code? Here we mentioned the dimension of the code is n comma k. Simply we stated n comma k. So we know what is n, small n. Small n means here the total number of bits in the block code. Okay, then k is the number of bits. So n comma k is the dimension of the code in the convolutional code. Okay, then how to we draw the code tree in the convolutional encoder? Okay, so here see that this is already we know this is the diagram of convolutional encoder. So this is the first bit or current bit. Then these two are the shift register, acts as a buffer or flip-flops, two flip-flops. Here, initially you assume these two bits are 0. Okay, initially you assume these two bits are 0. Okay, then how to represent the states of the encoder? Okay, so here two successive bits, message bits, previous message, that is M1 and M2 represents the state of the encoder. These two bits are going to state the state of the encoder. The input bits M affect the state of the encoder because the one by one we are applying the input bit, it will affect the state of the encoder because first shift it is moved to M1, in the second shift it moves to M2. Okay, so it definitely affect the state of the encoder. Okay, whenever a new bits is shifted to M, the contents of M1 and M2 define a new state. And the outputs X1 and X2 are also changed. Once here it will say, take a shift, then definitely the output also changed according to the new state of M1 and M2. Okay. So here how to say the state of the encoder. See that this is the M1 and M2. So M1, M2 it is 0, 0 now. The state of encoder is A. Okay, 0, 0 means the state of encoder is totally only we have 4 states. M1, M2 it is 0, 0 means A. Then 1, 0 means it is a B. Then 0, 1 means it is a C state. 1, 1 means it is a D state. Okay. 0, 0 A state. Okay, keep it in your mind. So this is used for solving the problem. Okay, the state of the encoder, it is M1 and M2. It is 0, 0 means A, 1, 0 means B. It is 0, 1 means G, C state, and 1, 1 represents it is a D state. Okay. Then how to develop the code tree. Okay, so here one example. The message sequence is 110. Okay, the input message sequence, it is 110. Assume initially M1 and M2 are 0, 0. Okay, so the first bit came means here it is the input bit is 110. Suppose initially the first M is equal to 1. The first bit came, then the first bit stored in the M. Okay, then so M is equal to 1. So initially we already told the M1, M2 are 0, 0. Okay. So M is equal to 1 and M1 is equal to 0, M2 equal to 0. Okay. So how to draw the first tree means here, see this diagram. Okay, this is the code tree diagram of convolutional encoder. So here the initial state we already told it is 0, 0 because the first initially the M1, M2 was 0, 0 and M is equal to 1. Okay. So 0, 0 state means it is a state. Oh, so it is start with A. So initially it start with A. This upward arrow indicates the message bit M is equal to 0. So the first bit, suppose M is equal to 0 now, it indicates the upward arrow. Okay. M is equal to 1 means then it indicates the downward arrow, it is 1. Okay. So here it start with initially A and it is the node state or node. Then this upward arrow indicates message bits it is M is equal to 0 and downward arrow indicates message bits M is equal to 1. This is the next state. Okay, so this is the taking the first shift. What is the next state of the encoder? Okay, so this is the new state of node when M is equal to 1. Okay, so here see that initially it is the first bit 1, M1 it is 0, M2 is 0. Okay, so what is the output of this one? Because X1 it is equal to M modulo addition of M1 modulo addition of M2. So M plus M1 plus M2, here taking the XOR operation. Okay, so XOR operation means same inputs are 0 now, the output is 1. Okay, if different inputs now, the same inputs now, the outputs are 0. Then different inputs now, the output is 1. Okay, so for example, here 1 plus 0 plus 0. Okay, so here 1 plus 0, this is both are different. Okay, not the same input. So different input means output is here it is 1. Then again 1 plus 0. So these two are also different inputs. So the output is 1. Okay, same input in the XOR gate means the output is 0. Different inputs in XOR gate means the output is 1. So this is the condition. Okay, so here it is 1 plus 0 plus 0, it is equal to 1. Okay, then x2 is m modulo addition of m2. So already we know. So m modulo addition of m2 means it is 1 plus 0. Here also the two bits are different. Okay, so the output bit is 1. Okay, then what is the next state? Because the first state is here, first input is 1, 0, 0. It will move to, it take one shift. Okay, first shift. First shift na, this 1 move to here, 0 move to here, this 0 discarded. Okay, so here, so this M1 move to M1 and then 0 move to M2. Then 0 in the M2 and the bit is discarded. Okay, so this is the new state of the convolutional encoder. So 1, 0 means it represents the state. 1, 0 means what is the state? Here M1, 1 and M2, 0. 1, 0 means the state is represented as the B. Okay, so the first shift, the encoder move to A to B. Okay, so first state, initial state 0, 0, that is A, and the next state 1, 0, it is B. So after the first shift, it goes to the B. So that's why this diagram indicates A to B. What are the output bits? It is 1, 1. So already we calculated the output bits are 1, 1. The input state A, output state, new state is B. So the start with A state, it goes to B state and the output bits are 1, 1. Okay, so likewise in each shift we can draw the code tree. Okay, so this. Then the next bit also 1. Okay, so the new state of encoder is now, it is 1, the x1, here the first, initially the x1, x2 are 1, 1, it is transmitted to the output register. It contains the shift to write by 1 position as shown. Okay, then the new state of encoder is M2, M1. M2, M1 is 0, 1. That means M1, M2 means it is 1, 0. It is the B state and outputs are transmitted and x1, x2 are 1, 1. Okay, then input bit is M1, then the next state it is B, the outputs are 1, 1. Okay, so this is the first one. In when the next shift, okay, this is M1 is the first bit, so the second bit also 1, yeah, 1, 1, 0. So initially we see the message sequence is 1, 1, 0. So okay, so already 1 came, then the second one come to the operation. Okay, so here the second bit 1, the contents of shift with register with this input with filo. So already we have second bit it came now. Here it is 0, 1, 0 in the previous state. Okay, so second bit 1 came now. The M is equal to 1, so 1, 1, 0. Okay, so 1, 1, 0, it takes the next shift. Now this one move to here, this one move to here, 0 discarded. Okay, so this is the next state of second bit. Okay, so the new status, it is 1, 1. 1, 1 means the new status D. Okay, because 0, 0 means A, then 1, 0 means it is B, 1, 1 is the new status D. Okay, then the outputs of this status 1 plus 1 plus 0. Here both bits are same. Okay, so the input bits are same means the output is 0. Then again 0 plus 0. The both bits are inputs are same. So the output is 0. Okay, then here 1 plus 0. The both input bits are different. So the output bit is 1. Okay, so what is the output of this state? It is x1, x2, it is equal to 0, 1. Okay, then new state is 1, 1. Then it is a D state. The output bits are 0, 1. New state is a D. Okay. So likewise, we can calculate the code tree diagram up to the last bit is 0. Okay. So 1, 1, 0. Okay. So we can see the next problem in the next video. Okay. Thank you.